If you spend any time watching AI developers online, you've probably heard the term vibe coding. The idea is that you simply hack away at a prompt, throwing instructions at a chat interface until, almost like magic, a working application snaps together. But inside top-tier engineering teams, that chaotic image is replaced by a reality of structured, CLI-first development. There's a massive chasm between a fragile script that works once for a demonstration and a resilient, semi-autonomous AI agent capable of running reliably in a live network environment. High-velocity development relies on tools like the Claude Code CLI to automate the setup and maintenance of these rigid engineering environments, removing the friction of manual configuration. To see how this actually operates, we are going to build a production-ready AI agent from first principles. Our goal is to architect a system that can handle complex security vulnerability triage. Before writing a single line of code, we must adopt the core philosophy of this workflow. We are abandoning monolithic chat interfaces and moving into highly controlled software environments. This diagram illustrates the necessary architecture. A true agent requires 5 layers: a planner as the reasoning engine, a tool executor for external systems, a memory layer for context, a policy engine to enforce rules, and a feedback loop for evaluation. Relying solely on a foundation model's innate knowledge without building out this architectural scaffolding guarantees that the system will fail when exposed to real-world unpredictability. The first step is validating whether the agent is actually worth building. We need to identify a specific, repetitive decision loop. In our case, the exact steps a security analyst takes to assess a new threat. Once defined, those 5 conceptual components translate into a physical project structure. Logic blocks map directly to directories for prompts, tools, memory, evals, and configuration. Engineers initialize these environments entirely through a command line interface to ensure the setup is reproducible and strictly organized. Notice the prompts folder. Here, we encounter the practice of treating prompts as code. Instructions are no longer typed loosely into a text box. They are saved as deterministic, version-controlled markdown files. These files don't rely on polite conversational language. They contain explicit reasoning steps and rigid operational constraints that the model must follow precisely. Using the CLI, we run tests against these files to refine the agent's planning behaviors in isolation before connecting the system to any live data. By treating prompts as versioned software artifacts, we guarantee that the reasoning engine will behave consistently across thousands of automated runs. But a reasoning engine on its own is effectively paralyzed. Without external tools, a language model is a static text generator confined to the data it was trained on. To give the agent capabilities, we build tools as isolated modular Python scripts. As shown here, separate scripts for tasks like scanning vulnerabilities or querying a database connect directly into a central configuration registry. Registering these scripts in the configuration file explicitly tells the agent exactly what actions internal environment. Before the agent is granted access, we execute these tools directly through the CLI. This verifies that the baseline scripts function correctly, independent of any AI involvement. However, granting an AI the ability to execute code and modify live systems introduces severe risk. This is where the policy engine becomes critical. We hard-code specific guardrails directly into the system's governance layer. This includes mandating human approval checkpoints for sensitive actions and enforcing a strict mathematical limit on the total number of actions the agent can take per run. With tools and rules in place, the agent needs to maintain context. A persistent production agent requires a structured memory system to track information across multiple sessions. This diagram maps the 3 layers of agentic memory. The top lane represents short-term state, continuously tracking immediate context of the active task. The middle lane introduces a vector database, serving as long-term memory, storing unstructured data as mathematical clusters. When the agent encounters a specific problem, it queries this database to automatically retrieve historical context and known remediation steps without needing to be reprompted by a human operator. The bottom lane generates the event logs. This creates a rigid, immutable audit trail documenting every single decision, tool call, and outcome. Engineers use the CLI to manually inspect these logs or inject critical new knowledge directly into the memory streams to correct future behavior. Without this multi-layered memory architecture, an agent is incapable of learning from its failures or justifying its logic during a security audit. All of these components, the prompts, tools, and memory, come together in the core execution cycle. This is the heartbeat of the autonomous agent. Looking at the logic flow, the cycle begins with a foundational while loop that continuously runs as long as the task remains incomplete. In the first phase, the planner block synthesizes user input alongside memory data to formulate a strategy. The agent maps that logical plan against its internal registry, selecting the specific tool required for the current step. During execution, the chosen script runs against the live environment, returning data or making an approved system change. The result of that execution is permanently written back into the memory system. Finally, the agent enters a reflection step, evaluating the execution result against its original goal, determining if the task is finished or if it must iterate again. It is this highly structured, self-evaluating mechanism, not the raw processing power of the underlying language model, that creates autonomous behavior. To ensure the agent remains predictable after deployment, its logic must be tested against a comprehensive evaluation harness. To stress test the system, engineers write rigid, YAML-based evaluation scenarios, creating hundreds of simulated tasks like complex compliance checks. This evaluation dashboard tracks the outputs of those tests, generating precise quantitative metrics for overall accuracy, tool execution correctness, and the rate of model hallucination. Alongside accuracy, the system continually logs operational constraints, specifically monitoring the latency of each action and the computing cost per run. In this environment, automated, quantitative metrics provide the only reliable proof of production readiness. When you combine this deep instrumentation with command line tooling, you experience the real speed of this workflow. It isn't a lack of structure. It is the ability to run, observe, and tweak a highly engineered system in a rapid, frictionless iteration loop. To move this agent off a local machine and into reality, the deployment stack relies on standard software practices, using containerization and Kubernetes orchestration to scale the infrastructure. In production, any failures or user overrides are captured by the observability layer and fed back into the prompt updates and evaluation datasets, driving continuous learning. Success in agentic AI follows the same path as traditional software development, building deep memory layers and modular tooling to transform a reasoning model into a resilient system.